And then we go. Hello and welcome back to part 2 of min-max 15.7. Since these problems were not long enough, let's make them even longer by introducing the boundary. You see, what's happening now is, let's say you had some kind of a shape that has this hill in it, right? I'll have to redraw this, so give me a second. There we go. No. All right, so this is some kind of a shape, and we do know how to find the max point here use the above procedure. But now if you look at the boundary of the problem, it too has a max, a min, another max, and so on. Aha! So now, in addition to calculating everything we calculated earlier, we get to calculate, luckily now it's Calculus 1, calculation along the boundary to try and get the min and max along those as well. Now, I want you to think of a cookie cutter. You have dough that it's pretty much flat everywhere, and then you press the cookie cutter in it, and the cookie cutter makes those edges. The edges are going to be the vertical walls. You can think of the desk over here, and you can see how it has a vertical drop downward. Now, the cookie is not going to be perfectly flat. It's going to have min and max, many of those. So the highest of all maximum values on the top of the cookie, which is not a perfectly glass or ice, like smooth, flat surface, one of those absolute max values could be on the boundary or could be inside. So the procedure we covered so far is detecting all of the min and max values within the object. What we are learning now, the red stuff, we are going to learn how to check for min and max on the boundary if the problem is bounded. So for that, I'm going to work out problem 52. It gives you the function fxy, which is a very simple x squared plus y squared minus 2x minus 2y. On the region with vertices 0, 0, 2, 0, and 0, 2. So what kind of the domain do I have? What is this domain? What shape is the domain? What is bounded by these three vertices? It's a 5th grade question. Triangle, thank you. Holy nightmare. So, triangle and we draw that triangle. 2 units this way, 0, 0, 2 units this way, boom. Think of a cookie cutter in a shape of a triangle. You press that into a dough, you get a triangular cookie. Now, that cookie, brownies are cut like that, like triangles, right? Okay, fine. And now you have, well, baklava is definitely cut that way, but that might be too much of Slavness for you, noobs. Well, you, I don't know. No? Baklava should be awesome. Yeah. It's Mediterranean, but it also, no. You should, because my, one of our colleagues, no, we'll tell you also. Anyway, so you have your cookie dough, which is this, and now it cuts. Now, we do the problem to find all min-max values inside the triangle. So we have our 2x minus 2, fy is 2y minus 2, fxx equals to 2, oh, that's larger than 0 right away, fyy equals to 2, fxy equal to 0. This is so fast. 2x equals 2x equals 1, 2y equals 2y equals 1. D at 1, 1, very quickly, is 4 minus 0 larger than 0. fxx larger than 0. We have a minimum at 1, 1. Minimum at 1, 1. 1, 1 is actually on the edge. We should be also able to detect that 1, 1 with the procedure that we are going to learn. So now let's see in purple. Now let's do blue. What's the new boundary? What I have when I look at my triangle, I'll draw this larger so we can see. 1, 2, 1, 2. So what I have here are 3 equations. This side is y equals 0. This side is x equals 0. And this side over here is y equals negative x plus 2. So I have 3 equations which bound my shape. Now, I have to calculate, because I have 3 sides and 3 equations, I have to calculate 3 Calculus 1 optimization problems along each one of the sides. So, for y equal to 0, we have our f of xy, which was x squared plus y squared plus, no, minus, right? Minus 2x minus 2y. When y is equal to 0, this turns into just f of x, being x squared minus 2x. And it becomes Calculus 1 problem. So you take the derivative, you get 2x minus 2, you set it equal to 0, you get x equals to 1. You get x equals to 1, and now you plug that in. So there is something happening at x equals to 1, right? Now that is along this line here. So at x equals to 1, I'm getting something. So, I mean, we know also that y is equal to 0, so it's y is 0. So I have a point 1, 0. So now I find f of 1, 0, and that will give me 1 squared plus 0 squared minus 2 times 1 minus 2 times 0 to be negative 1. I have a point 1, 0, negative 1. I have to store this because remember what I'm going to do. I'm going to find all of the points that are min-max values along the edges and then see which one has the highest z, which one has the lowest z. The one with the highest z is the absolute maximum, is the tallest point on the cookie, and one with the lowest z is the minimum point of the cookie. So now I am done with y equals 0. Next one we can do x equals 0. So for x equals 0, that's the next calculation, we repeat everything the same. I have my f of x y, which is x squared plus y squared minus 2x minus 2y. When x is equal to 0, kills all the x's. So now I just have f of y. And f of y is y squared minus 2y. And when I differentiate, I get 2y minus 2 equal to 0. Y equals to 1. X equals to 0. So something is happening at 0, 1. Calculate f of 0, 1. So that's 0 squared plus 1 squared minus 2 times 0 minus 2 times 1 gives you negative 1. And we have 0, 1, negative 1. 0, 1, negative 1. So we found another point on the boundary. And as you can see, the z value is the same. It's a negative 1 like before. Final part here. For y equals negative x plus 2. So that's going to be along that cross line. And that's, remember, our main method detected the maximum there, right? Now this one is going to have some calculation because our fxy is x squared plus y squared minus 2x minus 2y. We need to plug in this value. So now, since you are getting rid of all the y's, you are only getting a function of x. That's going to be x squared. And now you have plus negative x plus 2 squared minus 2x minus 2 times, and the y is negative x plus 2. So you simplify this and you repeat again calculus 1 optimization. So f of x is equal to x squared plus x squared minus 4x plus 4 minus 2x plus 2x minus 4. So f of x is 2x squared minus, because these guys cancel as well, so minus 4x. Take the derivative of this. F prime is going to be 4x minus 4 equal to 0, and here it is, x equals 1. Since you have x equals 1, you plug that into the other equation. Y equals negative 1 plus 2 gives you another 1, and you get a point 1, 1. That's the point we detected earlier. You see it over here? That's the point we detected earlier. So now I'm going to calculate the value for this. F of 1, 1 is going to be 1 squared plus 1 squared minus 2 times 1 minus 2 times 1. And we are going to get negative 2. So this point is 1, 1, and negative 2. So now I was able to determine 3 points. There is a point 1, 0, negative 1. There is a point 0, 1, negative 1. And there is a point 1, 1, negative 2. This is the lowest z value, therefore equal to, I'm just going to put, so lowest z value, so it's absolute minimum. There are no points that are lower than the z value of negative 2. That's what this calculation gives us. If you have a bounded object, you are supposed to plug that boundary into your main equation for the shape, and that will reduce that equation down to a Calculus 1 problem, because you killed the dimension. Right? When we said x equals 0, we killed x. When we said y equal to 0, we killed y. When we said y equals x plus 2 or x minus 2 or whatever it was, we killed y again. So when you plug the equation of the boundary, you will kill one of the dimensions. And the problem transforms from a Calculus 3 problem into a Calculus 1 problem. And you will be able to just solve calculus. Now, obviously, for square, you're going to have 4 edges, rectangle 4 edges, triangle 3 edges, trapezoid 4 edges, circle just 1. You plug in x squared plus y squared equals to 9, right? You plug that in. Obviously, it's going to be unclean with calculations and so on, but no matter what the boundary is just the shape of what you have, which is why I want you to think of a cookie cutter. It's a shape that is pressed on top of the object to give it the boundary shape of what it is. And again, min and max can happen along those edges. It doesn't have to be min and max somewhere in the middle, right? If you are to, I don't know, tie a piece of cloth over there and stretch it down, one end this way, one end that way, you would create a plane, right? That plane would have a maximum point in the corner, right? So it could be on the boundary. It doesn't have to be in the middle. Doesn't have to be in the middle. So now you go home and you just do, 500 of these problems, and I'll see you in like 4 years. If you're going to do the 500 problems, and that's how long it should take. See you tomorrow.